In a single-phase 120/240 volt service, the question arises whether neutral conductors should be counted as current-carrying conductors when derating. The answer is yes, under certain conditions. According to the National Electrical Code, specifically Article 310.15, the neutral conductor of a 3-wire, single-phase circuit must be counted as a current-carrying conductor if the major portion of the load consists of nonlinear loads. Nonlinear loads are electronic devices such as computers, LED lighting, variable frequency drives, and other equipment that draw current in short, sharp pulses rather than a smooth sinusoidal waveform. These nonlinear loads generate harmonic currents, primarily third harmonics, which add arithmetically in the neutral conductor. This can cause the neutral conductor to carry a significantly higher current than the phase conductors. When the neutral conductor carries a higher current than the phase conductors due to harmonic currents, it must be counted as a current-carrying conductor for derating purposes. Derating refers to reducing the allowable ampacity of conductors based on the number of current-carrying conductors in a raceway, cable, or directly buried to prevent overheating. The National Electrical Code, NEC, provides tables that specify ampacity derating factors based on the number of current-carrying conductors. The NEC Table 310.15 code outlines the adjustment factors for more than 3 current-carrying conductors in a raceway or cable. Thusly, it is crucial to identify whether the loads connected to the single-phase 120/240 volt service are predominantly nonlinear. This can be determined by assessing the types of equipment connected to the circuit. If the load consists primarily of incandescent lighting, resistive heating elements, or other linear loads, the neutral conductor does not typically need to be counted as a current-carrying conductor for derating. Secondly, if the loads are determined to be primarily nonlinear, the neutral conductor must be counted as a current-carrying conductor. In this case, the total number of current-carrying conductors, including the neutral, must be considered when applying derating factors from NEC Table 310.15 current. For example, if a circuit consists of 2 phase conductors and a neutral conductor that carries harmonic currents, all 3 conductors must be counted as current-carrying conductors. If these conductors are installed in a raceway with other current-carrying conductors, the ampacity of all conductors must be derated according to the table. Thirdly, it's important to note that the NEC provides an exception for certain situations where the neutral conductor does not need to be counted as a current-carrying conductor. This exception applies when the neutral conductor only carries the unbalanced current from phase conductors and does not carry significant harmonic currents. In such cases, the neutral conductor is not counted as a current-carrying conductor for derating purposes. However, this exception is becoming increasingly rare due to the proliferation of electronic devices and nonlinear loads. Fourthly, to accurately determine the current flowing in the neutral conductor, a true RMS ammeter should be used. A true RMS ammeter measures the actual root mean square value of the current, which accounts for harmonic currents. A standard ammeter may not accurately measure the current in the neutral conductor if harmonic currents are present, leading to an underestimation of the actual current. Fifthly, when derating conductors, it's essential to select the appropriate conductor size based on the calculated ampacity after derating. The conductor must be sized to carry the load current safely without exceeding its temperature rating. NEC Table 310.16 provides the allowable ampacities of insulated conductors rated up to 600 volts, based on their insulation type and temperature rating. After applying the derating factors, the selected conductor must have an ampacity equal to or greater than the calculated load current. Sixthly, in addition to derating conductors based on the number of current-carrying conductors, it's also important to consider other factors that can affect conductor ampacity. These factors include the ambient temperature, the presence of thermal insulation, and the type of raceway or cable used. High ambient temperatures can reduce the ampacity of conductors, and NEC Table 310.15 bone provides correction factors for ambient temperatures other than 30 degrees Celsius, which is 86 degrees Fahrenheit. Seventhly, when conductors are installed in thermal insulation, their ampacity must be derated to prevent overheating. The NEC specifies derating factors for conductors installed in thermal insulation depending on the type of insulation and the proximity of the conductors to the insulation. Eighthly, the type of raceway or cable used can also affect conductor ampacity. Some raceways, such as rigid metal conduit, provide better heat dissipation than others, such as electrical non-metallic tubing. The NEC specifies allowable ampacities for conductors installed in different types of raceways and cables. Ninthly, it is important to consult the latest edition of the National Electrical Code (NEC) for the most up-to-date requirements and guidelines for derating conductors. The NEC is updated every 3 years, and changes are made to reflect new technologies and safety concerns. Local codes and regulations may also have additional requirements that must be followed. Tenthly, it is also a good practice to label the panel with the adjusted value. This can help to avoid problems with any future electrical work done to the service. In summary, when dealing with a single-phase 120/240 volt service, the neutral conductor must be counted as a current-carrying conductor for derating purposes if the major portion of the load consists of nonlinear loads. Accurately assessing the load type, measuring neutral current with a true RMS ammeter, applying appropriate derating factors, and selecting the correct conductor size are crucial for ensuring a safe and compliant electrical installation. Always refer to the latest edition of the National Electrical Code and local codes for specific requirements and guidelines. Understanding these factors is crucial for ensuring the safety and reliability of electrical systems. Failure to properly derate conductors can lead to overheating, insulation damage, and potentially fire hazards. Remember to prioritize safety and consult with a qualified electrician when in doubt. The presence of harmonic current significantly impacts the neutral conductor, especially in modern electrical systems with numerous electronic devices. To further elaborate on the impact of harmonic currents, consider that these currents are multiples of the fundamental frequency of the power system, which is typically 60 Hz in North America. The third harmonic, which is the most common harmonic found in single-phase systems with nonlinear loads, has a frequency of 180 Hz. Unlike the fundamental frequency currents, which tend to cancel each other out in the neutral conductor of a balanced three-phase system, the third harmonic currents act arithmetically in the neutral. This means that the neutral conductor can carry a current that is significantly higher than the current in the phase conductors, even if the load is balanced. The increased current in the neutral conductor can lead to several problems, including overheating, increased voltage drop, and premature failure of the neutral conductor. Overheating can damage the insulation of the conductor, leading to short circuits and fire hazards. Increased voltage drop can cause equipment malfunction and reduce performance. Premature failure of the neutral conductor can result in a complete loss of power to the connected loads. To mitigate the effects of harmonic currents, several strategies can be employed. Firstly, harmonic filters can be installed to reduce the amount of harmonic current flowing in the system. Harmonic filters are designed to block specific harmonic frequencies, thereby reducing the overall harmonic distortion. Secondly, K-rated transformers can be used to supply power to nonlinear loads. K-rated transformers are designed to withstand the additional heating caused by harmonic currents. Thirdly, oversized neutral conductors can be installed to accommodate the increased current flow. The neutral conductor should be sized to carry at least 1.73 times the maximum phase current in systems with significant harmonic distortion. Fourthly, dedicated circuits can be used for nonlinear loads. This helps to isolate the harmonic currents and prevent them from affecting other equipment connected to the system. Fifthly, power factor correction capacitors can be used to improve the power factor of the system. Power factor correction capacitors can also help to reduce harmonic currents. Sixthly, it is important to regularly inspect and maintain electrical systems to identify and address any potential problems caused by harmonic currents. Regular inspections can help to detect overheating, insulation damage, and other signs of harmonic-related issues. Seventhly, using shielded cables and proper grounding techniques can help to minimize the effects of electromagnetic interference caused by harmonic currents. Shielded cables can prevent harmonic currents from radiating into the surrounding environment, and proper grounding techniques can ensure that harmonic currents have a low impedance path to ground. Eighthly, consider using active harmonic filters. Unlike passive filters, active harmonic filters inject current waveforms into the system that cancel out the harmonic currents. This approach offers more flexibility and effectiveness in mitigating harmonic distortion. Ninthly, implement load balancing techniques to distribute the load evenly across the phases. Balanced loads minimize neutral current, reducing the potential for harmonic-related issues. Tenthly, utilize modern power quality monitoring equipment to continuously assess harmonic levels and system performance. These monitors provide real-time data, enabling proactive identification and correction of harmonic problems. In addition to addressing harmonic currents, it's important to consider the impact of voltage imbalance on the neutral conductor. Voltage imbalance occurs when the voltages on the three phases of a three-phase system are not equal. Voltage imbalance can cause excessive current to flow in the neutral conductor, even in the absence of harmonic currents. The NEC requires that voltage imbalance be limited to a maximum of 3%. If the voltage imbalance exceeds this limit, corrective action must be taken to reduce the imbalance. Corrective actions may include redistributing the load, replacing faulty equipment, or upgrading the electrical service. Furthermore, consider the impact of single-phase converters on neutral current. Single-phase converters, commonly used in electronic devices, draw current unevenly from the power source, leading to increased neutral current. To mitigate this, consider using three-phase converters or distributing single-phase loads evenly. Ensure compliance with IEEE 519 standards, which provide guidelines for harmonic control in electrical power systems. Adhering to these standards helps maintain power quality and prevents harmonic-related problems. Implement a comprehensive power quality management plan that includes regular monitoring, analysis, and corrective actions. This proactive approach ensures the long-term reliability and efficiency of the electrical system. Furthermore, it is crucial to understand the impact of neutral to ground voltage on sensitive electronic equipment. High neutral to ground voltage can cause malfunctions, data errors, and even equipment damage. Proper grounding techniques and equipment selection can minimize neutral to ground voltage. Consider using isolated ground receptacles for sensitive electronic equipment. Isolated ground receptacles provide a separate grounding path that minimizes noise and voltage fluctuations. Regularly test and inspect grounding systems to ensure their effectiveness. A properly functioning grounding system is essential for protecting equipment and personnel from electrical hazards. Furthermore, be aware of the potential for neutral conductor overloading due to unintentional parallel paths. Unintentional parallel paths can occur when multiple grounding connections are made to the neutral conductor, leading to increased current flow. Avoid creating unintentional parallel paths by ensuring that only one grounding connection is made to the neutral conductor at the service entrance. Also, it is beneficial to use dedicated neutral conductors for sensitive electronic equipment. Dedicated neutral conductors provide a lower impedance path for return current, minimizing voltage drop and noise. Consider the use of active neutral current cancellation systems in facilities with high levels of nonlinear loads. These systems actively monitor and cancel out neutral current, reducing the load on the neutral conductor. Moreover, understand the impact of energy-efficient lighting on neutral current. While energy-efficient lighting, such as LED lighting, consumes less power, it can also generate harmonic currents. Choose energy-efficient lighting products that are designed to minimize harmonic distortion. Regularly monitor the temperature of neutral conductors and connections to identify potential overloading or loose connections. Overheated conductors and connections can indicate a problem that needs to be addressed. Implement a robust preventive maintenance program for electrical systems to ensure their long-term reliability and performance. A well-maintained electrical system is less likely to experience problems related to harmonic currents or voltage imbalance. These preventative measures should be combined with periodic reviews of the load profile and connected equipment to maintain the best possible safety measures for the electrical system.